Architect Meera Milan Ajit. She is currently working as a senior architect at L&T Construction, Buildings and Factories. She has worked for various commercial and institutional projects for the Engineering Design Research Centre, ranging from shopping malls, IT parks to metro rails. She has attended many national conferences and seminars. She has also worked as a freelancer in Chennai for various projects.
Welcome to UGC lecture series in architecture. I would now be taking you through Earthquake Resistant Architecture AR 6008 lecture 4. Before starting, while learning about this particular subject, we always say be prepared, be aware, be ready. So this subject teaches you to be prepared and be ready, and also lets you be aware of the facts regarding earthquake and helps you design something that is earthquake resistant. In the first 3 lectures, you would have seen what is an earthquake, how an earthquake is caused, what are the various factors that leads to the earthquake, what are the various factors that happens because of the earthquake. You would have learned various terminologies regarding the earthquake. You would have understood what are the various other calamities that can occur as the aftermath of the earthquake. You would have understood how various plan and the site selection would help us create a better seismically designed building. You would have also learned about how a symmetrical or a systematic or a normal simpler plan can be better for earthquake resistance rather than a very different or elaborate plan. Moving on, in this particular lecture, you would be seeing the part 3 of the unit 2, that is site planning, performance of site and buildings. So in the previous lecture, you would have seen part 2 of this particular lecture, wherein you would have I spoke about the various ways by which the single masonry wall or a single wall and just a wall enclosure without the roof stands the earthquake and how that sustains the earthquake. In here now, in this particular lecture, you would be seeing other various structural or building types or wall types, structure types, and how they would react to the earthquake and how they would behave when struck by the earthquake. So the contents of this particular lecture is the roof on 2 walls, the roof on wall enclosure, roof and floors, and also this lecture introduces you to the next chapter, that is the introduction to seismic design codes. So as I said in the previous lecture, behavior of various types of building structures, equipments, lifelines and collapse patterns as what we see in this particular unit, that is unit 2. And as you saw again in this particular lecture, you can see that this building actually is for giving up to the earthquake and falling on another building, that actually creates a stacking and everything collapse on top of each other, creating a larger debris and a larger issue. Now we will be seeing what will happen if there are 2 walls, not an enclosure, and there is a roof. So there is no enclosure, it is just 2 walls and a roof. This picture shows a devastating earthquake that happened a few years back, and how everything fell on top of each other. So now in this picture you can see 2 walls, that is both B's, not these 2 walls are not attached to each other, they are standing on opposite, they are like sitting on the opposite sides, and so they are both B's, there are no A walls, and then on top of that there is the roof. So in the figure, a roof slab is shown to be resting on 2 parallel B walls, and the earthquake force is acting on the plane of the walls. If you can see, this is the earthquake force that is happening on the plane of the walls. So assuming that there is enough adhesion between the slab and the walls, that is adhesion as in assuming that there is enough stability or enough mortar or enough whatever is sticking the wall and the roof together, that is strong enough, assuming that is strong enough, the slab will transfer its inertia force at the top of the wall B, causing the shearing and overturning actions in them. So what happens is, when something is resting on top of something, that something kind of transfers its load and kind of tend to take support from what it is sitting on. So the roof, that is the heavy roof that is sitting on top of this, and it's completely strongly like connected to each other, that is strongly bonded to each other, the adhesion is strong. Then what happens, when the roof gets the earthquake on it, the inertia that is created inside the roof, that roof tries transferring it to the corners, the top of this particular walls. So that what happens, so then the roof is as such safe, it won't crack, but this will create an overturning action in the walls to which that inertia is transferred. So to be able to transfer its inertia force to the two end walls, the slab must have enough strength in the bendings in the horizontal plane. So this action of the slab is known as the diaphragm action. Reinforced concrete or reinforced brick slabs have such strength inherently, and that acts as a rigid diaphragm. So what happens, the slab should be strong enough, and that shouldn't, the moment an inertia acts, an earthquake acts on the roof, that slab usually, if it is very thin and it's not strong enough, that bends first. So but then if that is strong enough, like a reinforced brick concrete or the reinforced brick slab, then that will be strong enough, and that will have enough strength to transfer its inertia into the walls that is holding them. However, the other types of roofs or floors such as timber or reinforced concrete joints with brick file covering will be very flexible. So that means those walls, those slabs easily give up themselves, and they won't bother or try transferring their their inertia into the walls that is supporting them. They themselves give up and they crack. The joints will have to be connected together and fixed to the wall suitably so that they are able to transfer their inertia force on the wall. As I said before, the adhesion between the wall and the roof is very important. Then that has to be strongly adhesive or strongly fixed together, so that the joints will be connected enough for the inertia to be transferred to the support. At the same time, the wall B must have enough strength as shear wall to withstand the force from the roof and its own inertia force. So what happens when the earthquake strikes? These walls will have its own inertia acting on it. So as long as this particular wall doesn't act as a shear wall, what happens? They bend. Because of the inertia that is coming from the top of the roof to the corner of the wall, as well as the inside inertia that is happening on the wall, they try to overturn. So as if this wall is strong enough and acts as a shear wall, then that wouldn't happen, and they will have enough strength to withstand their own inertia as well as the inertia from the roof of the wall. Moving on to the next particular section, that is roof on wall enclosure. So now what we saw previously, first we saw just a wall, then we saw just a wall enclosure, then we saw two walls and a roof, and now we are seeing an enclosure and a roof on top of it, and then what happens. So now consider a complete wall enclosure with a roof on top and subjected to earthquake force shown acting in the x-axis. So if you can see in this particular diagram, you can see this is the wall A and there is another wall A here. So there are two parallel A's, there are two parallel B's, and then there is the roof, and then you can see this is the x-axis, the y-axis, and the earthquake force is acting along the x-axis. As per the diagram, you can see on top the earthquake force is acting towards the x-axis. If the roof is rigid and that acts as a horizontal diaphragm, its inertia will be distributed to the four walls in proportion to their stiffness. So what happens? The roof is completely adhesed to the wall, all the bonding is really strong, and the roof is able to transfer its inertia, strong enough to transfer its inertia into the supporting walls. What happens is, if the roof is almost entirely is rigid, and that, so then the horizontal diaphragm or the roof will transfer or distribute its inertia to the four walls in proportion to the stiffness of those four walls. So it will equally distribute or distribute it based on the stiffness of all four walls and how much they are. The inertia of the roof will almost entirely go to the walls B, since the stiffness of the wall B is much greater than the walls A in the x direction. In the x direction, since the stiffness of wall B is stronger than wall A and the earthquake force is acting towards the wall to the x direction itself, what usually happens is that if the roof is rigid, they would almost entirely distribute the stiffness or the inertia into both the parallel B walls, not the A walls. So in this case, the plate action of the walls A will be restrained by the roof at the top and horizontal bending of wall A will be reduced. On the other hand, if the roof is flexible and the roof inertia, then the roof inertia will go to the wall on which it is supported, and the support provided to plate action of wall A will also be little or zero. So already there is a plate action that is happening on wall, and so that will be restrained by the roof because that is not transferring load to that particular wall in the first case that we discussed about. But if in case the roof is not as rigid as we discussed and it is flexible, then what will happen in turn would be that the inertia would be going to all the walls which supports the particular roof, and the plate action for wall A will be be little or zero. The support to the plate action would be zero. Again, the enclosure will act as a box for resisting the lateral loads, and this action decreasing in value as the planned dimensions of the enclosures increase. The next thing that we will be seeing is roof and floors. So we already saw wall enclosure. We saw wall and roof, we saw wall enclosure and roof. Now we will see roof and the floor. So roof is coming, floor is coming, and then what happens? So an earthquake induced inertia force can be distributed to the vertical structural elements in proportion to their stiffness, as we discussed before, provided the roofs and the floors are rigid to act as horizontal diaphragm. If you can see in this particular picture, earthquake force 1 is acting, there is a floor, there is a roof. So if the roof is rigid, if the floor is rigid, then as we said, the horizontal diaphragm action happens, and they split their inertia equally into the wall that has the maximum capacity or the shearing capacity. Based on their structural strength, they will be getting the loads, based on which the building will actually withstand it and stay. So in here, this is the B, these two are the parallel B walls and these two are the parallel A walls. So what happens otherwise is the roof and the floor inertia will only go to the vertical elements on which they are supported. So they kind of completely split, and then the smaller wall kinds of, the weaker wall kinds of gives up and the building collapse. So therefore, the stiffness and integrity of roofs and floors are important for the earthquake resistance. The roofs and floors which are rigid and flat are bonded on and tied to the masonry. They have a positive effect on the wall, such as the slab or slab and beam construction can directly cast over the walls, and jack arc floors or roofs provided with horizontal ties are laid over the masonry walls through good quality mortar. So others that simply rest on the masonry walls will offer resistance relative motion only through friction, which may or may not be adequate depending on the earthquake intensity. So what happened? It is very important for the roofs and the floor to be rigid, and they should be bonded really tight with the masonry wall, as in the adhesiveness between them should be really strong, and also the roof and the floor should be strong. Then only this horizontal diaphragm action can happen, and equal splitting based on the strength of the walls can occur. If not, what happened, if it is very flexible or if it is very simple roof, what happens, that can only react through friction, and that if the earthquake intensity is less, it may be able to withstand, but if it is more, it may not be able to withstand. So now we will be moving to the unit 3, that is seismic design and building configuration. So, in this particular lecture, we will be seeing part 1 of this particular unit, and we will basically be learning what are the seismic design codes and what does that say, and what are the seismic design codes in India and what does that say. So, when an earthquake strikes in a particular area, what happens is from the roads to the dams to the bridges to the buildings, everything collapses. So, once that happens, became like a regular occurrence in a particular country or a particular area, any country usually divides that particular country into seismic zones, usually in 4 seismic zones, and each seismic zones, as we said in the first lecture, will define how much prone is your area to the earthquake. There are really highly prone areas in a country as well as really less prone areas in the country, based on which are the codes designed for those areas of the country. So, basically the experiences in the past, the history and earthquake history that happened in the past has demonstrated that many common buildings and typical methods of construction lacks the basic resistance to the earthquake forces. So, when the earthquake strikes, if we have a simple building or a normal building that we usually construct without understanding the seismic load and the seismic problem that actually happens, those kind of, and when we design a building, what happens is such kind of a building may not be able to withstand the earthquakes like the other building that is actually designed for the bearing the seismic load. So, this kind of things has actually happened before, and that's the reason why the government of much major countries have come up with the seismic laws for construction. So, in most cases, this resistance can be achieved by following simple, inexpensive principles of good building construction practice. So, not everything comes with, needs to be very expensive to do. So, this is a very small step towards your own safety and the safety of the society and the safety of the people. So, for that, architects are usually pushed or encouraged to use to understand the codes or seismic design codes, codal provisions, and design buildings based on that, at least in the seismically prone areas, so that the much higher damage due to the earthquakes can be avoided. Adherence to these simple rules will not prevent all damages in moderate or large earthquake, but life-threatening collapses should be prevented and damage limited to repairable proportions. So, what happens when a very major earthquake strikes is that all the buildings give up, people die, all their lively procession goes off, and everything. There are much things that are irreversible that happens because of the natural calamity, but such things can be reduced and the irreversible things can be avoided, and reversible things might happen which actually can be repaired and bring back to how it was originally. So, first and foremost thing that we should understand while understanding the seismic design code, especially of India, are the seismic zone. So, there are basically 4 seismic zones in a place, that is zone A, zone B, zone Z and zone D. Zone A is a risk of widespread collapse and destruction happens in that particular area. When an area is highly prone to the earthquake, then that area would be under zone A, wherein there is high risk of widespread collapse and disruption of that particular area when and if an earthquake strikes. In the zone B, you can see there is risk of collapse and heavy damage that can happen. So, as you see from zone A to zone D, the risk factor reduces, and zone Z is almost very minor damage and much lesser risk. So, in zone B, there is heavy damage and collapse can happen, but the amount of destruction would be much lesser than what would be in zone A. The hilly areas, the mountainous areas where there is earthquake, which are prone to earthquake, would be under zone A. In zone B, it will be prone to earthquake, but then it might be a flatter area wherein the landslides can be avoided. In zone C, the risk of damage is there, but then the collapse and destruction can be avoided. And in zone D, there will be very minor damage. There can be damage, but that will be very minor like. So, the extent of specified earthquake strengthening should be greatest in zone A, and for reasons of economy can be decreased in zone C with relatively little special strengthening in zone D. So, importance of building. For earthquake resistant design, you always should categorize a building into different sectors. One is where like there will be maximum public, there will be a lot of people, and there will be always a lot of people accumulated in that particular area. And two other ordinary buildings wherein they are like there won't be many people all the time, all throughout the day in that particular area. So, the important buildings are the hospitals, the clinic, communication buildings, fire and police stations, water supply facilities, cinemas, theatres and meeting halls, schools, dormitories, etc. And ordinary buildings are nothing but housings, hostels, offices, warehouses, factories, etc. So, bearing capacity of foundation soil. As we discussed in the previous lecture, in the lecture 2 actually, the soil variety in a particular site and how a soil responds to the earthquake and how that gives up or that withstands the earthquake is what is actually a major factor in deciding on the site of a earthquake resistant or a building based on from the seismic parameter point of view. So, there are 3 types of soil that we are seeing based on our seismic understanding. One is a firm soil, the other one is a soft soil, and the third one is a weak soil. A firm soil is nothing but they have an allowable bearing capacity of more than 10, and they're very strong, and once built upon them, they kind of not give away your building because of them. The building might fall, but that may not be because of the soil, because the soil at that particular area is really firm. Then there is a soft soil, and these soils have allowable bearing capacity less than or equal to 10. That is, they are moderate. They can give up, but then they can withstand depending on the intensity of the earthquake. And then there is weak soil, and these soils are liable to large differential settlements or liquefaction during an earthquake. And that actually liquefaction, as we discussed before, is nothing but when the ground when it mixes with the groundwater, and the solid soil slowly becomes liquid, and there is a liquefaction of soil that happens, and because of which they tend to pull down the building, make it sink into it in that particular area, and that happens in weak soils a lot. So, buildings can be constructed on firm as well as soft soils, but it will be dangerous to build them on weak soils. Hence, appropriate soil investigations should be carried out to establish the allowable bearing capacity and nature of the soil. Weak soils must be avoided and compacted to improve them so as to qualify as firm or soft soil. Plan of the building, as we discussed before, the plan of the building matters a lot in earthquake resistant design, and the very linear building should be avoided, asymmetrical building should be avoided, many of the unsymmetrical projections should be avoided, and longer buildings is better if broken into compartments and compartmentalized into different buildings. The next is fire resistance. It's not usual during earthquakes that due to snapping of electrical fittings, short circuiting takes place, or gas pipe leakage may develop to leaks and catch fire. But fire could also be started due to kerosene lamps and kitchen fires. So, all these things can happen during the earthquake, and fire resistance hence is very important in the areas that are prone to earthquakes, because of the earthquake, when fire happens, if fire happens, it's very difficult to extinguish the fire. The fire hazard sometimes could even be more serious than the earthquake damage that happens. Because the earthquake might be minor, and because of which many repercussions might happen, fire might be one amongst them, and because of other things that is happening around, it is very difficult to extinguish or control the fire. So hence fire may cause more damage to the area rather than the earthquake, because it can't be stopped. The building should therefore preferably be constructed with fire resistant materials. So this table shows the categories of buildings for strengthening purposes. If you can see, in category 1, we have important buildings on soft soil in zone A. In category 2, we have important buildings on firm soil in zone A, important building on soft soil in zone B, an ordinary building on soft soil in zone A, and so on. So seismic zones A, B and C are important buildings, and moving on to the last and the major factor that affects the stability of a building during the earthquake, that is the foundation. For the purpose of making a building truly earthquake resistant, it will be necessary to choose an appropriate foundation type for that particular building. A foundation type is usually, they are directly proportional to the load bearing and to the ability of the soil, and what is the soil bearing capacity of the soil, and what is the soil in that particular area. So since loads from the typical low height building will be light, providing the required bearing area will not be usually a problem. For choosing the type of footing from the earthquake angle, the soils may be grouped as firm and soft, avoiding the weak soil unless compacted and brought to soft and firm condition. So weak soil can be taken in and they can be compacted and made to a soft or firm soil. But usually while choosing the foundation, always better to go for designing a building, earthquake resistant building especially, it's better to go for sites where the soil is firm or soft. So hence, based on that, the foundations are designed, and foundations shouldn't be shallow, and it should be deep enough so that liquefaction doesn't happen on top of the foundation. While discussing the firm soil condition, any type of footing, individual or strip type, can be used. It should of course have a firm base of lime or cement concrete with requisite width over which the construction of the footing may start. It will be desirable to connect the individual reinforced concrete column footing in zone A by means of RC beam just below plinth level intersecting of right angles. And in soft soil, it will be desirable to use a plinth band in all walls where necessary. It's necessary to connect individual column footings by means of plinth beams as suggested above. It may be mentioned that continuous reinforced concrete footings are considered to be most effective from earthquake considerations, as well as to avoid differential settlements under the normal vertical loads. So summary of this particular lecture is, we saw how roof on two masonry walls respond to the earthquake, and that is understood. We understood how the roof would transfer the load if the adhesion is good between the roof and the wall to both the walls, and if the wall has enough shearing capacity, then it might withstand the inertia from the roof as well as by itself. We saw the performance of wall enclosure with roof for earthquake resistance, and that was discussed, and we understood how the roof transfers the wall, the load maximum based on the shearing and the bearing capacity of each of the walls, in equally distributed based on that. We saw how enclosure with roof and floor respond to the earthquake, and that was discussed, and we understood that if the roof and floor was strong enough, then and the adhesion between the roof floor and the walls were strong, then they would distribute it equally to the walls based on the bearing capacity of each walls. We also saw the Indian Seismic Code, and that was introduced, and all the major considerations in the code for earthquake resistant construction is discussed and understood. Moving on to the questions. How does a roof on two walls behave during an earthquake? How does a roof on wall enclosure behave during an earthquake? Elaborate. How does roof and floor respond to earthquake? Elaborate. What are the considerations for seismic design as per the Indian codes? Discuss in detail. In the next lecture, you would be seeing how each type of building, based on the maybe masonry building, wooden buildings, all these react to the earthquake and how cracking happens, how they can withstand. What are the positive and negative of each building materials from the seismic point of view, and how that is used in the buildings, and how that can be used for designing and coming up with a positive solution to create a better seismically efficient building. Thank you.